Hi, so I was recently browsing the eBay listings of one of my favourite recycling companies, from which I've got quite a few interesting teardown items, and I came across this. This is an iris scanner, and I've done iris scanners before, but I just got a feeling this was something a bit more than just a normal camera. I was a bit busy at the time. I'd had a very quick look around on the net, and it just looked like it might be something vaguely interesting, so I just chucked a bid on it and basically forgot about it. Ended up winning it, and then what I didn't notice on the listing, it was collection only because of the size, and unfortunately this is up the other end of the country. But fortunately Mark, who runs the Dexter's Lab 2013 YouTube channel, who does very similar sort of teardowns to me, lives quite closely, so he kindly offered to go and pick it up and sort of take all the large casing parts over it to get the whole thing down to a more sensible size to get down to me. And he shot a bit of video just to give an idea of the size and the construction. So over to Mark.
Hey everyone, this is Mike's next teardown. The problem is it's here in my house and it needs to go down to Mike. Now the problem is, as you can see, it's rather large. So what Mike has asked me to do is try and take this apart, disassemble it enough so I can put it in a box and send it down to him. What I'm going to do is just go quickly around this so you can get an idea on what this thing actually is and how big it is before it gets dismantled. So this is a biometric ID scanner, sort of thing you see in airports with the automated passport barriers, that kind of thing. So that's why it's so big, because it has to be as tall as people to be able to scan their faces. So it's a widge under 2 meters tall. The chassis is all pressed steel. These top and bottom covers come off, and there is a sort of chassis thing on the back. You got a couple of optical things going on here. I think that's a screen, and we got the camera view plate there, and I think there might be an infrared emitter in there to illuminate the subject in question. And here you got its ID plate. So it's manufactured by Aoptix. It's called an Insight VM iris recognition system. Model number is AB1012C. Right, so I've just laid this down flat so I can actually disassemble this. So as you can see, we've got the main chassis here, and we have what looks like the processor in here, and then some cables which run up to the top section. Right, so that's the top cover off. There's a few bits and bobs actually mounted to the cover there. There's what looks like the screen and that infrared illuminator, and then we have the optical bit. So I'm just going to quickly remove all this and we'll get it boxed up.
So I've now got this here on the bench in pieces. Now I've tried firing it up, but it doesn't really do anything particularly interesting. There was a hard disk on it which was removed by the recycling company, so I think that's the main reason it doesn't appear to do anything. But pretty much all it does is fire up some very fast loud fans and light up the LCD backlight, and there's some RGB status LEDs. And so it doesn't really do anything. I've had a probe around with a scope. There is a VGA connector on like an access panel behind, but nothing appears on that. So I think we're just going to have to take this thing fully to pieces. Here's the Optics assembly. Now this is clearly a lot bigger than just a camera. I thought it might be something just like a camera vertically with a mirror, just to allow a larger lens, but actually it's something rather a lot more interesting going on in here. So as you can see, there's some quite complex optics going on here. The first thing the incoming image hits is this mirror, and this actually is an XY swivelable mirror. There's a camera and a beam splitter here, so I think this is taking a fairly wide angle of view to find where the face is in the image, and then it sort of can point this mirror to get that centered, and then use a much narrower field of view to capture the actual iris image in high resolution, because you need quite high resolution images, probably focused to get accurate iris recognition. But there's also an interesting optical system here. The beam splitter sends one optical path through to this camera here, and the straight through path goes through a couple of lenses, bounces off this, which it turns out is like an adaptive mirror, which actually can change its curvature based on the amount of power fed into the coil. It's like, I think it's similar to a speaker voice coil, and you can just see the mirror there, which I think that's just like a fairly thin film, like a plastic film. So the image sort of comes through here, bounces off this mirror, and then we then have another beam splitter here. One image goes to this camera and the other image goes down to this one. And looking at some of the details in the patent, it makes reference to this being a wavefront sensor. So this is actually used as a feedback to the adaptive optic system to get the image accurately in focus over quite a wide range of distances, different people's heights. The spec says it'll work with anything from like somebody 7 feet tall to someone in a wheelchair. It's actually got a fairly large volume which it can actually aim and focus and get an accurate iris image. Right, I've taken the sides off of this just to get a clearer view of the optical components. This camera, instead there's labels on here, says ACQ camera, which would be acquisition, iris camera, and WFS camera, which is the wavefront sensor presumably. And each of these use a fairly simple little camera board, which they all look the same. It's got a Micron MT9V032 VGA sensor, which outputs serial LVDS data, so they're using a single Cat5 cable for power, probably I2C, and the image data. I had a poke around these. I couldn't see any signals because the whole thing wasn't really starting up, so couldn't see any signal. I've taken some of the back off of this so that I can actually use like a webcam board just to get an idea of what the field of view of these cameras is. So I'll do that once I've taken the camera boards off these other two optical assemblies. So I'm just going to use this webcam board, which you can see has got a fairly similar sensor size, so it should have a fairly comparable field of view to the original cameras. So this is the view through the acquisition camera. I'm sort of standing about sort of 2 feet away, and as I swivel the mirror you can see that swinging around over a sort of fairly wide field of view. So obviously what it's going to be doing is it's going to be moving this mirror, so as the person sort of moves across, it's going to be sort of keeping it centered, and we expect to see a much sort of a much narrower field of view on the iris camera, so we'll try that now. Right, so I'm really struggling to get the iris camera in focus. What I've done, I've just set up this torch with a piece of foil over it to give a nice sharp image, and I've got it sort of vaguely centered. Now if I put some current through that adaptive optics thing, you see it actually goes into focus as I adjust the current. That's about 1.3 amps. It goes in and out of focus. The curvature of that surface is changing to adjust the lens focus, but you can see from that's filling the image with a subject that's around an inch or so across, so that sort of means you pretty much get a whole iris in shot. Well, I've given up trying to get an image through this path. Everything is just so critical. I can't really get anything stable enough to get a sensible image, but so I think it's reasonable to assume it's designed to give an image, pretty much full center image of the your average eyeball. In terms of the actual sensors, the iris and the wavefront sensors seem to be pretty much the same. There is a different label on this, the wavefront one, but the sensors look the same. I can't see any, for example, anything like a lenticular array or anything on that, so I think this is a fairly normal optical sensor. The optical components are slightly different. There's this lens. All these lenses seem to have coatings on them. I think one of the issues I was having is that as well as the main beam splitter, this looks like it's dichroic. It lets visible light. It's very reflective to visible light but transparent to infrared, and the camera module that I was using had an infrared cut filter, so it was a bit hard to get a good image through there. And I think some of these optics may also have they've certainly got some coatings. They're sort of funky colours, and it looks like there's a flat lens inside there, and then this convex lens there on the outside, and then it also passes through this plate. Maybe a filter, but I think may also have something to do with the wavefront sensing. Again, I don't really know enough about optics to comment. I'm sure if you know all about this stuff, please leave some information in the comments. So let's take a look at this adaptive optics thingy. It's a bit reminiscent of a speaker, but I suspect it's more complex than that. I think it has some sort of positional feedback, as the connectors on the board had sort of drive and sense marked on it. It's got 4 pins. The main actuator is 8 ohms, so again sort of pretty similar to a speaker. Okay, I've taken this out of the mount, and you can actually see this is actually not unlike a speaker. There's a coil wound on this sort of the gold aluminium, I think there's a bobbin, and I think there's a magnet passing through the middle. Yeah, in fact you can feel the screwdriver retracting it. And there's a clear diaphragm which is mounted here, and as the magnet's pulled it sort of stretches this diaphragm to make it either bow inwards or outwards. It's a little bit hard to see, but if I sort of get the fluorescent light in the view, if I put some current through, you can see it moving, actually bending slightly. If I reverse the polarity, goes in the other direction. So it does actually come out apart quite nicely. So you've got the inductor here, the assembly with the magnet, and the diaphragm here. Now I'm not quite sure how the sensing works. There are 4 wires that come out of here. I wonder if it's just something like a 4-terminal sense to measure the voltage across the coil. I can't see anything obvious unless it's maybe a coil that they put some AC through to sense the position of the magnet perhaps, but that would probably be also affected by the excitation fields. I don't really know how that works, but I mean the focusing is probably a closed loop through the wavefront sensor, unless I suppose the other thing, it might be a temperature sensor perhaps. The temperature sensor, if I just measure the resistance, if I put some current through the coil, you start seeing the resistance going down to just an NTC thermistor in there, just to make sure it doesn't overheat. Now here's the scanning mirror assembly. It's a very nicely made unit. You can just about see there's actually some actual bearings in there. It's lightly sprung to a centre position. It's quite heavy, so this wouldn't be particularly useful for things like high-speed laser scanning or anything. And so you can see there's 4 coils around here. On the back there's a couple of small boards with a little multi-turn pot there, so I'm guessing there's going to be some sort of feedback arrangement where it can actually sense the position to give some closed loop. The fact that there's a set of 3 wires coming from each one of these, so I think there's going to be some sort of sensing going on in there. So let's see if we can see how that works. Well, this is actually surprisingly complex. On the back of the mirror thing we can see this cube reflector. There's what I think is a laser diode here which goes down. There's a little right angle mirror at the bottom, so it's firing the beam beam across there, goes across to here, and there's another mirror at the bottom, then comes out to this device on the bottom of the board, which is either a CCD or it might be a position sensitive detector, which is like an analog device that gives an output depending on where on the sensor the beam lands. So yeah, optical sensing obviously makes sense for this because there's no, you don't have any mechanical drag, but that seems quite a complicated arrangement, which is presumably done for accuracy and maybe speed. So we've got an awful lot of optics there for what is basically a sort of image find and focus type application. I can't help thinking that if you did this today, you could probably just use a high resolution image sensor and throw a bit of processing at it just to take a large high res image and actually pick the details out of it. Maybe something like a liquid lens autofocus or even a mechanical autofocus. The dates in this look like about 2010 manufacturing date, so yeah, the design may be older than that. So let's just take a look at the electronics now. Now this board is on the side of the optical assembly, and it's fixed down with a slightly ludicrous number of screws. Presumably that's just to stop the PCB flexing as connectors are plugged in from the other side. There's 1 or 2 unused connectors here, in particular these say intrusion detection jumpers. So obviously on a security type system you might want to have some sort of alarm if someone tries to take the cover off, but that wasn't fitted on this version. Curiously, there's a couple of read relays there, not quite sure what they would be used for. There's a Xilinx FPGA. This is going to be handling the video data. And here's an FTDI FT2232 and a couple of RS485 drivers. There's a couple of RS485 ports on the bottom of this. I think one for a card reader and one is for just some general purpose interfacing, so that'll be what that's doing. This is the infrared illuminator. This is sort of pretty straightforward. It's a big array of high power infrared LEDs on aluminium PCB. And just the driver board, this should be a load of switch mode converters to provide constant current through those LEDs. There's an I2C I/O expander there, so that's probably just controlling the sort of on-off state and maybe power levels through an I2Cs. And all these boards seem to have an E² prompt, which has just got a serial number in there. This is the display, nothing too exciting, it's just a bunch of RGB LEDs either side. When I powered this up, these were going all sorts of weird different colours. I think maybe these are a bit crozzled. In fact, if you look at the LEDs themselves, they do look a bit, they don't look particularly happy, and also the silk screen looks a bit discoloured. I think maybe this has run a bit too hot and the LEDs have died. And on the back there's just the backlight inverter. There's a CCFL backlight, so just standard backlight inverter board on there. So let's take a look at the main electronics unit. This is the back. This is a removable service panel which has got 2 USBs and a VGA connector. Presumably that's going to be for a keyboard and mouse and a monitor, and the space here for a 2.5-inch hard disk, which unfortunately was removed before I got it, so I think that might be why it doesn't start up. And some connectors down here for various I/O, control panel, card reader. It's probably like an RFID or a Megastripe card reader for you have a card and person type security. Alarm miscellaneous connector, 3 buttons down there, and a input switch and circuit breaker. There's also an Ethernet connector down here. This thing's mostly very well built, except for this little bodge. For these big connectors, instead of like retention clips or screws, they've just sort of silicone them. Seems a bit odd. Maybe looks like there are actually positions there for the clips. I wonder if maybe the this was designed for a different casing, and they found like the traditional clips didn't fit, or they couldn't get the connectors with the right clip detail or something. But seems a little bit odd. You know, everything else seems to be done sort of fairly well, but they just silicone these connectors in, which just seems a real mess. Now, looking at the top of this unit, we've got power supply on top. This is a modular multi-output power supply, fan at each end, big main board along the bottom, and a couple of boards sort of sat on top of sort of daughter boards on top. This, I suspect this is probably an off-the-shelf sort of PC on a module type unit, and the bottom is probably fully custom. So it's power supply, so it's a modular supply, 2 lots of 24 volts at 10 amps, 48 volts at 10 amps, and 12 volts at 10 amps. And this is various connectors to go to various different parts of the system. Here, great big mains input filter, and there's a board on the top here with lots of adjustments. I think this goes to the XY scanning mirror, so it's probably the scan driver board, and then just a bit of metalwork, and then the main board's underneath. And there's a heatsink on the back of here, and I think this is the drive for the XY mirror. It says on the board current stroke PSD, so PSD is probably the position sensitive detector to sense the position of the mirror. There's just a load of adjustments and op amps on this top board, and this will be the power driver stage with a couple of stereo audio amplifiers which will be driving the voice coil. There's a couple of analog multipliers here and pots for scale and offset, so this is all basically analog stuff, so it's turning a voltage into a mirror position. Here we've got this board which I think is in charge of certainly the adaptive optics. There's another stereo audio amplifier, Class D amplifier here, which will be driving the voice coil. There's 24-bit A to D, there's various other analog stuff, but I couldn't immediately see any D to A converters, so maybe perhaps it's using PWM from the board below. Obviously there's lots of unpopulated bits, so this is clearly designed to drive various different product variants. So lots of analog stuff going on here as well, loads of op amps. And now we're down to the main base board. Some DC-DC converter modules here. There's 3 of these PLX PX8311, which are PCI Express to generic bus interfaces. There's actually 3 of these, so this is going to be a like a PC on a module type thing. We'll take a detailed look at that in a sec. It's made by Contron. So this is basically a complete PC on a board. So if you're designing something like this, you don't really want to have to design your whole, a PC. You just buy it in. So there's 2 FPGAs here, Spartan 3000s with some RAM. Next to them, there's some unpopulated sections here for some other RAM, plus the PCI bus interfaces. So I'm sure these will be to do with the image capture from the various cameras. There's another one here, which I'm sure this is going to be to do with the adaptive optics and the XY mirror scanning. parts on the board for all the various systems. There's a slightly bodged over memory backup battery here. Loads of unpopulated connectors. There's JTAG and spare I2C. There's a speaker output there and various other things. One interesting thing is for the FPGAs they've actually used configuration flash devices. I'm surprised they did that rather than just soft loading the FPGA from the PC to make it easy to update. Can't think why they'd do it that way. There's a load of, I think these are probably debug connectors. These are marked sort of CAM1 mem, CAM0 mem, so I wonder if these are actually debug connectors on the camera memory buses from the FPGA. Various just bits of buffering here. This is the area for the rear panel area, so you've got USB VGA and the SATA connector for the hard disk, and the rest is just sort of various random bits of support thing, like there's an I2C bus to parallel port thing there, which presumably controls various status things. There's a little 2-channel temperature monitor. Not a great deal else. One interesting detail, this is a sort of high frequency interboard connector. You've got all the pins on the outside, and then there's like a solid metal blade in the middle to give you really good ground reference and good signal integrity for high speeds. It's quite a common technique for high speed connectors. Whereas on this one to the PC, they actually put the grounding on the outside and the pins on the inside. And just looking at the layer count on this board, you can see there's a layer 1 indicator. Just about see some apertures in the board there, and if you look on the other side down to the bottom layer, this is layer 16, so it's a 16 layer PCB. So a very expensive board. And this is the PC module. These things are sort of very common. There's literally hundreds and hundreds of different variants of this, plus quite a few bus standards, but basically the idea is it's like a complete PC on a board for integration into other systems. We've got all the 3 Intel chips. I don't know exactly which flavour of Intel chipset this is. So it's made by Contron that do. It's one of the main companies that do these. But there's like many companies that make these in many different formats. There's 4 gigabytes of RAM on here. So we've got the main sort of processor and the support chips. All the power stuff here, and just the various support chips. There's even little PIC, there's a PIC 12F508 there, and there's a lattice CPLD there, just mopping up various logic functions. So there's that FFC connector. I'm guessing that's probably going to be for an LCD option, and obviously you've got very high pin count connectors here that basically break out everything that you'd want to connect to a PC out of these connectors onto your system. And just lastly, a quick look at this power supply. This is a 1200 watt power supply in a very compact case. 2 fairly powerful fans here. And like most other modular power supplies, you've got like a common front end module board, and then various modules for the various different output voltages. And there's sort of PCBs in all directions. There's some sort of funky magnetics going on there. There's the input filter. This is inside a cage because obviously if it's filtering noise, you don't want to capacitively couple that noise directly to the filter, so that's why there's this shielding can around it. There's also some conductive mesh or squishy stuff to get good bond onto the top plate. 2 input capacitors on little PCBs, and these modules, it actually says on here AC input 380 volts, 140 kilohertz. So you've got like a transformer for each of the outputs. There's some other sort of transformer here. I'm not really sure what's going on with that. It's a fairly small transformer, but look, there's wires that come out, and looks like that forms the primary of this main transformer here. There's a heatsink on here. There's a bunch of MOSFETs here, so that'll be a synchronous rectifier, an output inductor, a few capacitors, quite a lot on the bottom side of the PCB, some isolation slots. But yeah, it's a very compact design. And there's a sort of bus bar on the output, so obviously these are all the positive outputs and this is a negative output. They probably need a negative output for the voice call drivers for the Aoptix stuff. And the rest control connections as well. I'm guessing these 2 outputs are parallel, so these wires will probably be for controlling the voltage tracking so it knows it's connected to another output. So that's another crazy complicated bit of gear. I saw mention that some of these were installed in London Gatwick Airport in 2011, and say the dates on this are around the sort of 2009 to 2010, so that's the sort of vintage. I'll suspect that a modern version of this can probably dispense with a lot of the optics and just replace it with a high-res camera and throwing more processing power at it. There might still need to be a certain amount of optics, but I'm pretty sure it wouldn't need anything like this much to achieve the same thing. And I'll put a link to the patent covering this in the description if you want to read a bit more about the technical details.